Last time we had talked about the velocity and tangent problems. The purpose of those problems was to introduce the idea of a limit process. We can just call it a limit. And essentially it was this idea that as the time interval went closer and closer and closer to zero, the average velocity got closer and closer and closer to the instantaneous velocity. Today, we are going to talk about limits of functions, just so that we can get comfortable with how they work with very basic math objects. So the notation that we're going to use when we talk about a limit is lim with an x and an arrow going to a that says the limit as x approaches a, and we will write some function that we'll call f of x. This will be our informal definition of a limit. There is a formal definition of a limit, but it's not something we need to talk about right now, because what I want to get across is understanding of what a limit is. If a limit exists, we say that it equals some number. We're going to write limit x approaches a, f of x. What does this mean? Sometimes we're going to have functions that do have limits, and sometimes we are going to have functions that don't have limits. If the limit exists, we say that as x gets closer to a, the value of f gets closer to a fixed finite value L. Okay? So this is going to be our working definition of a limit. And there are three things here that I want to address. So the first one here I'm going to put in blue as the value of x gets closer to a, so I'll put that as 1. The second one I'll say the value of f gets closer to a fixed value, and then the third one I'll say some finite value. So I'm going to spend a moment to talk about all three of these because they're all important and they will all lead to your understanding of what a limit is. If a limit exists, the best way to think about it is a picture. You've got some function of x. There's a location right here, a. A limit is asking you to walk along the graph of the function like it's a bridge. As you walk closer and closer to that location, you are asking what are the heights of the function doing? Do they get closer to any value? So to try to illustrate that, let's consider the first point here. As x gets closer to a. So I'm going to draw three little examples of graphs, and they're going to look fairly similar, but in each case there'll be one difference. The three functions, they all look somewhat similar. There's something happening at the value of a for each one of them. If I were to write down f of a, in this particular case, the value of the function at a is like asking what's its height. So here its height is L. In this case, the height of the function is m, because that's where the solid dot is. And in the last one, the value of the function is undefined. There's a hole at L, which means there is no value of the function there. Sometimes we will put DNE for does not exist. Now we're going to talk about the limit. The limit of a function says walk along the function like you're walking on a bridge, and then ask yourself, what height are you getting closer to? And in the first case, if you were to put your left hand and your right hand on the graph and walk closer, the function is like a bridge that wants to take you to a height of L. So we say that as you get closer and closer to A, the height takes you closer and closer to L, the limit exists. In the second example, if you're asked about the limit of the function near A, same thing. You put your left hand and right hand, you imagine walking along the function like it's a bridge, and you walk closer and closer and closer to this location A. As you get closer and closer to A, the height of the bridge wants to take you closer and closer to L, same height as it was before. You might say, well, but there's a hole there and then there's a drop. That doesn't matter. The limit doesn't care about what's happening at A. It just says as you get closer to A. And that's a huge difference. That was the whole 0 over 0 business we talked about in the last class. So I'm hoping then in the last situation, you're able to see the value of the limit exists and it's equal to L. It's the same. And so one of the major points here, the value of f of a has no influence on the limit as x approaches a. All that matters is what's happening near x equals a, not at x equals a. The next important thing is that the value of f gets closer to a fixed value. And so the best way to understand something like this is with a picture. In this course, we are going to see piecewise functions a whole lot. So a piecewise function tells you what the output of the function is doing and where it's doing that. So let's say I've got a function, it's going to be a height of -1 when I'm less than 5, and it's going to be a height of +1 when I'm greater than 5. So you need to be able to understand what a function like this looks like. So when x is less than or equal to 5, the height of this function has to be -1. Now I'm going to put a fill dot at 5 because the function is equal to -1 at 5. When x is greater than 5, I've got a height of +1. What's the limit of this function as x approaches 0? So if I were to get closer and closer to a location of 0, the closer I get to 0, the closer and closer that the height of the function gets to -1. If I were to say, what's the limit as x approaches 7? No ambiguity. The closer and closer I get to 7 and I walk along this blue bridge, it takes me to a height of +1. What's the limit as x approaches 5? And this introduces an important point and some new notation. This function is doing different things on either side of 5. And so we have to be able to understand that and deal with that. So when we are standing at 5 and we approach with the left and we use our left hand, we are going to have what's called a left hand limit. So we are taking the limit as x approaches 5, and then we're going to put a little minus sign to say that we are approaching from the negative side of 5. That's all that means. Use your left hand and approach from the left side of the function. So when I'm standing to the left of -5, I am on this part of the bridge. The bridge wants to take me to a height of -1. But if I stand on the right and I say, okay, let's talk about approaching that location from the right, we're going to talk about something called a right-hand limit. Approaching from the right means positive side of 5, so we are going to use this notation. X approaches 5, and we'll put a little plus sign. That's a right-hand limit. So you literally just put your right hand on the graph and get closer to 5 using only your right hand. As I get closer to 5, you should be able to see that the bridge wants to take you to a height of +1. And now the real issue here is that these two things are telling you different pieces of information. The sides don't match. So what is the limit equal to? In order for a limit to exist, both the left and the right side limits have to match. So in order for a limit to exist, the left and right limits must exist and match. And since they don't here, we are going to write down that the limit as x approaches 5 of this function does not exist. The one-sided limits don't match. So in order for a limit to exist, the one-sided limits have to match and exist individually and give you the same result.